Looking at our next topic, Charles's law. Right, for Charles's law, we know from our previous assignment that we were looking at the relationship between temperature and volume. Now, as you're filling out the notes, like I said before, just pause the video when you need to. So with temperature and volume, what we found was that, remember, the amount of gas and pressure had to be held constant. And so when you had a container full of gas, right, if you increased the temperature, then these particles started moving around faster and faster and faster. And so if we're going to keep the pressure constant, this container had to get bigger. So now there's more distance for the particles to travel before they hit the wall, and then they can keep the same pressure. So the volume gets bigger, more time for those particles, so the pressure stays the same. Okay, so Charles's law, you should have hopefully found in your last little assignment that when you had your graph, hopefully your data points came out pretty straight so that you picked that graph, right, that it was a linear graph, and that means that the volume and temperature are directly proportional to each other. So if you double the volume, you double the temperature. If you triple the temperature, you triple the volume. If you cut the temperature into an eighth, the volume would cut into an eighth. Right, so they are directly proportional to each other. Okay, if we increase the temperature, the particles move around more, which I said, and so to keep the pressure constant, the volume has to increase. So again, I tried to describe that if this is the shape of our container and they're moving around faster, well, if this causes pressure and this causes pressure and this causes pressure, right, every time it runs into a container, if we want that pressure to remain constant, well, when we increase the temperature, that particle moves faster. So if we make the volume bigger, now as it's moving faster, it takes longer to get to here and to get to here and to get to here. And so because it doesn't strike the container as often because it has further to go, it would decrease the pressure. Right, so as the temperature increases, the volume has to increase to keep that pressure the same. Or if you decrease the temperature, the volume decreases to keep the pressure the same. Now, there are different ways of measuring temperature. We measure them in degrees Fahrenheit here in the United States. The rest of the world measures everything in degrees Celsius, but the scientific unit of measurement is Kelvin. So we need to use Kelvin. Even if a problem gives all the numbers in Celsius, you have to convert it to Kelvin when you're doing the gas laws. So it's pretty simple. You can see that equation there, that Kelvin. Notice it's not degree Kelvin, it's just Kelvin. Kelvin equals degrees Celsius plus 273. So if we look at our first problem, if we want to convert 25 degrees Celsius to Kelvin, we're just going to plug that into the equation right there. And then that's simple enough. 25 plus 273, because we're using the rules for adding significant figures, they're both significant to the ones place, and so my final answer is significant to the ones place, 298 Kelvin, right? Not degrees Kelvin, just Kelvin. Now, if they happen to give you Kelvin, then you're going to plug it in the equation over here. Right, so we have 258 equals degrees Celsius plus 273. So we're going to subtract 273 from each side. And so 258 minus 273 gives us, whoa, I'm going the wrong way, gives us our answer. And again, we're accurate to the number, not sig figs, not 3 sig figs, but to the decimal place, or in this case, the ones place. So our answer goes to the ones place. The reason why we can't use degrees Celsius in equations is that you can have negative values for degrees Celsius, and so you can't have that. For Kelvin, there is no such thing as negative. At 0 Kelvin, that's the coldest there is. And when you have an atom that has all its protons and neutrons in the middle, and then you have this area where these electrons are moving around, at 0 degrees Kelvin, that electron stops moving. Everything stops moving at 0 Kelvin. Nothing has any kinetic energy at all. There's no movement. So you can stop here. The video will stop here, and you can go to the homework and you can do 3 quick problems on converting between Kelvin and degrees Celsius, and then you can check out the second video where we're going to move on to some 2 example problems for Charles's law.